are using the simplified version of this whole model, which is DSSC, which is dye-sensitized solar cell. So the only difference between DSPEC and DSSC is it uses chromophore instead of chromophore catalysis of milling. So it's much easier to study, and it just directly allows us to know the photocathode. So the P-type metal oxide platelets are very good material for this photocathode, which is my main goal of this project, my focus of this project. And standard material for this P-type material these days is nickel oxide, due to its best performance so far among all the material used. But it's not the best material because there are a lot of reasons. First, it has very low surface area, and it has like terrible carrier mobility, which limits the film thickness coated on the top of FDO, and it like leads to low load of dyes on it, and decreases the current production very low. It's very low, and also these all traits leads to very high recombination rate. So therefore, this whole system is very low efficient. So this is not very good material. Therefore, we are in search of new material to replace this nickel oxide, and the material we found is nickel cobalt oxide. So why did we choose this nickel cobalt oxide? There are many reasons. And first, it has higher mobility. So it allows us to have thinner films coated. We can load more dye on it. Leads to better light harvesting system, more current produced by that. And also, it doesn't suffer from visible light absorption, which nickel oxide does suffer. And this competes with dye absorption, so it lowers the efficiency of current production dramatically. Also, it has much higher dye absorption in there, and the one really nice thing about it is it starts off with high open circuit voltage, so it like starts at a better start line than nickel oxide does. So in order to study nickel cobalt oxide function in the device, I made it. So I got the method from the paper I found, and according to the paper, I put water, nickel chloride, cobalt chloride, and some tetramine base, and boiled it for 5 hours under reflux condition and blowing nitrogen gas constantly. And after that, I obtained a metal hydroxide phase of nickel cobalt hydroxide powder, and when I brominated, I got green nickel cobalt hydroxide layered double hydroxide form, and finally when I annealed it, I got the very black color powder. When the water would flow away, it just leaves nickel cobalt oxide powder. So this is a X-ray powder diffraction pattern of nickel cobalt hydroxide form, and you can observe this one really high peak compared to other noises here, and then I'll explain the significance like really soon. And this is X-ray pattern of the brominated phase, and when I compared these two graphs I got with the XRD pattern shown in the paper, I found the method of producing this powder. And as you see this, their pattern matches pretty well. So this means that I have the right powder according to the paper. And the one very high peak means something, which is textured material. The material I got is textured material, which means that it has two-dimensional structure. So the platelet shape of its structure has only top surface and bottom surface of it. And it means that that's the only surface area it has. So when in XRD, that's the only part the X-ray is diffracted, and that means the only one high peak of it. And this SEM images also show the platelets I got. So I don't know if you can see in this slide well, but you can see like perfect hexagonal structure platelet right here. Oh yeah, better. Perfect hexagonal structure right here. And this is means that it has really, really high surface area because of the pores and the fact that it's ultra thin. And with a high surface area, it can load more dye on it, about 300 times more than the plain bulk film. And therefore, the more dye you load on it, the more current you can get out of it. So basically, it means that better efficiency. Also, the 2D structure, the platelet structure, gives very long matter conduction pathways, which means that one carrier goes longer pathway before it jumps to the next platelet, so you have lower possibility of recombination, which also increases the efficiency. And after that, I made paste in order to test the device, so I added this powder into ethyl solution and homogenized with disperser, volatile, and cornsonicator, and placed FTO glass in the spin coating, and I coated it, and the coated FTO surface sit on the dye for 24 hours so that dye can be absorbed in the film surface. And this is the film morphology I observed, and it shows that there's still, the platelet shape survived over here. Some of them are crushed, but it still survived here, and then it's very even throughout the surface. So it means that film's coated really well, and still all the characteristics are there. And this also shows that there's porosity on each film, so all the benefits I got here is still alive in the film there. And I haven't tested the device yet due to this time limitation, but so far, in conclusion, I got new P-type microscale but ultra-thin platelets with high porosity for D-spec use. And this is a novel material found. And due to its high surface area, we're expected to have very high mobility. We haven't tested numerical value, but we are supposed to. And this all characteristics should lead to more efficient photocathode. Therefore, the novel material I found is candidate for an alternative P-type semiconductor for using D-spec device. And one little thing for further study, in XRD pattern, I found the material shown as mostly amorphous instead of crystalline due to higher noise, not one really high peak. So I had to find a method to go up to higher temperature than 550 degrees Celsius to make the material crystalline without destroying the platelet shape, so that it can perform much better in the actual device. And after that, I want to make a tested device. So how much efficient I got out of it. This is the reference I got. And I would like to thank you, my mentor, Dr. James Campbell, and Corey Flynn, President, and Dr. Halpin, Dr. Bruno from North Carolina School of Science and Math. Thank you very much. Any questions?
This is 2:15? Yeah.